Perfect. Nobody touches anything anymore. All right, cool. Everybody welcome in our Paretos office. First of all, I want to thank you that it's a big honor for me giving this talk to you and telling you something about my daily work and working with time series data, time series forecasting. So I'm really honored giving you this talk today. The name of my talk is, as you see it, Beyond Toy Datasets, time series forecasting for real business for real business problems. My name is Robert Haase. I'm a physicist, studied here in Heidelberg from bachelor's and master's. During my master's, besides working in condensed metaphysics, I was deep diving into forecasting models. Sorry for that. Okay. I don't touch anything. I was deep diving into time series forecasting a lot. Also, I was investigating and studying back in 2019 already transformer algorithms and also implementing my own transformer-based algorithms, brought them into production. And I think it was at that time that when I realized that there's great potential within those algorithms, namely being transformer-based or being any kind of deep learning technique, and that we should at able use them as well next to other more fundamental statistical methods or machine learning methods. Back in university, I was then very motivated to just use my knowledge about all this technology and then just go into the industry and just apply it. But then I brutally experienced two things. In reality, in real business problems, like Excel still seems to be the best practice. And secondly, the data sets I was working with then in industry were not as beautiful as they were in university. They were not like pre-processed for me. They had gaps. They had everything, but it was not nice. It was not that beautiful. So especially that last point motivated me to give this talk to you today, because I want to emphasize basically the differences that we see in real-world scenarios and also some concepts that need to be applied in order to cope with those real-world scenarios and with all those little traps that you can basically walk in. And basically what I want is the goal of today would be that you understand the basic concepts, the basic ideas of, if you ever find yourself in the situation of coping with time series forecasting problems, you do understand the basic concepts and ideas of it, and you'll be able to avoid those pitfalls and just turn your use cases into a success story. Yes, so I think Fabian's already said, gave us a small outline about Paretos itself. For me, working as an AI scientist here, why I see our approach as superior is because we don't stop at purely implementing or deploying machine learning models itself. We don't stop at the prediction itself. We want to use the predictions and put some optimization on top of it in order to not only do the predictions, but also enable decision makers to be able to do optimal decisions on top of our artificial intelligence. I think, sorry for that. Yes. I think it's very important to leverage to help decision makers making optimal decisions within complex environments, and this is what we at Paretos strive for. All right, let's look at our outline. First of all, I want to give you a brief introduction into time series forecasting in general. Afterwards, Fabi, kannst du gucken, ob du ein anderes Docking Station findest, bitte? Secondly, I want to talk about to go from toy data sets to real-world business problems. I will explain later what I mean with toy data sets, but I think this is a very important distinction we should make here. And third, but not last, I want to give you some ideas of how modeling in real-world scenarios does look like. What are the things, the pitfalls that you have to be aware of in order to turn use case into success stories, and also especially in the give you some examples in the analysis of what you need to take care of as well. So first of all, probably you all know this guy for our international spectators. Okay, this is Günther Jauch, one of the big German quiz masters or show masters, and he's asking you the following question. And I want you to take out your phone, or I don't know if you have pen and paper with you, and just type in what is the first and most important step when doing time series forecasting. Okay, we have answer A, which would be the hyperparameter tuning. So if you run a machine learning model, you need to optimize it. We all know that, so definitely important. We have running the baselines, meaning running some simple models as well next to some other models. Might help you, might doesn't help you. I don't know. C would be use the latest state-of-the-art models. We all read about transformer models, we read about NLP-based models, multi-layer perception models. Maybe also always being up to date can definitely help you with the results. Or D, ask ChatGPT, what am I actually doing here? So please write down your question. I will reveal in the end what's my right answer at least. Okay. Ich glaube, gerade funktioniert es, aber lass mal hier. Ah, shit. Yeah. All right, that was good. Sorry, I just changed my docking station. Yes. This is not right. Display settings over. Duplicate slideshow. Sorry. Does anybody know where to click here? Which one? Right click. Yeah. Yes. Almost. I see it very good. Okay, perfect. That is perfect. Thank you for, thanks for being so patient with my technical issues. You know, deep tech is not always that easy. All right, I wanted to give you a brief overview about what time series is about. Actually, it's quite easy. You're basically, what you're doing is you're predicting some future observations based on your historical values. I mean, time series, normally it's not that widely spread in, it's not like a classical machine learning technique or like an area, but we see those time series basically in every company because every data that is tracked over time can basically in the end be implemented and formulated as a time series problem. Where we see the most, the biggest leverage is, for example, in e-commerce companies where they sell, like they have a big e-commerce shop and they sell 10, 20,000, sometimes 100,000 different products, and they need demand for every single product in order to make their supply chain effective. So knowing the time series, the demand in this case upfront, is a big advantage for their business. Secondly, we also see, for example, finance is, for example, stock forecasting, all that stuff that is tried, sometimes more successful, sometimes without any success. But these are classical areas of time series forecasting. Let's don't get distracted too much by the whole mathematical definition. All I want to show you is basically that we do predict some targets Y based on some feature matrix X. We can therefore also, since we predict multiple targets at the same time, we can basically explain the time series forecasting as a multivariate regression problem, where you just predict multiple targets at the same time. What is important is what kind of features do you have? You do have, for example, the KPI itself. If you want to predict the future demand, you have to take your historical demand into account. You can take historical features into account, meaning was your stock filled at that point in time or not? These are important information in order to predict the demand accordingly. Also, what is important is, for example, future information, future covariage, which are denoted by this. For example, is there a sales day upcoming? What will be the weather tomorrow in Heidelberg or in 3 days in Mannheim? These are all important information that we need to take into account in order to make this prediction more accurate. So now I brought you a really simple example, which is the air passengers dataset. The air passengers dataset is just the data where the air passengers being tracked, how many flights were taken between the years 1949 and 1961. And as you can see, this is one of the datasets that is often used for benchmarking your models. So you see, if you read papers in this area, you see a lot of times, okay, let's benchmark on air passengers. There's also other typical benchmark sets like Boston house prices. This is what you read everywhere in the papers. So these time series, not all of them, but most of the times, they do have some simple characteristics that we can fit for. For example, here we want to characterize the trend of the time series. We see there's a clear trend, there's a clear upwards trend in this scenario. So this is like one thing that we have to fit. The other part that we have to try to characterize is the seasonality. So we see just before Christmas, the air passengers increases. Therefore, this is the seasonality part. The ultimate goal, basically, of time series forecasting is to identify trends, seasonality, but also the influence of external information. There are, like I said, other benchmark sets, the air passenger set, the Boston house prices. So this is what I was working on in academia, and this is what I refer to as a toy data set. It's only a single time series, not often super complex, but it has some characteristics that can be fit by normal time series approaches. But what we see in real life is that real life data sets, they're just different beasts. And I mean, they sometimes can look dangerous, they can bite sometimes. But today, I want to give you an idea of how to cope with them, even though they look like that. Okay, first of all, one of the biggest differences is in these real-life time series datasets, we see tons and tons of multiple heterogeneous datasets, meaning you can have arbitrary many datasets, data points, products in a portfolio that can exceed 100,000 of SKUs that all have to be predicted separately. And when I say there's a lot of data, there is really a lot of data. And then there's data everywhere. Okay, so really, just imagine we have 2 million or maybe 200,000 SKUs times the historical part of 2 years on a daily frequency. It's like 200,000 times 730 days data points. This is a normal amount that you have to expect when working with real life data sets. What we also see is we have a lot of data sets, for example here, data spikes that are really driven immensely by external factors. So if you look on the left, there are also data spikes, but you can extract them, you can characterize them by the seasonality part, by looking at historical values. Here, we know, for example, here there was a sales day. So we have time series peaking up within 1 or 2 days and then drastically falling afterwards again. And this is all being influenced by external factors. So we have to take external factors into account, and we have to find the right models to take them into account in order to really come up for a proper demand prediction. Another one is the cold start problem. Cold start problem means there are products, time series, demand, whatever, where we have no to only less historical data for that. Just imagine you have a product launch here of a product that you never sold before in your shop, in your e-commerce company whatsoever. But you need to have like a picture in your mind, or like a roundabout number of what will be the demand. And just imagine you are sitting here on this pink line, and you know only that you sold nothing until now. What do? You can imagine it's hard. It's hard to get a proper prediction for that, but there are techniques. Last but not least, we see a lot of intermittent time series in real-world scenarios. Intermittent time series are time series where they consist mainly out of zeros. There is no clear seasonality or trend defined, and the data that you see here is more or less just noise. So it's hard to fit any kind of seasonality or something. It's really only that, and you have to cope with that. Since we see these time series a lot in different areas, I want just to have a little bit more deep dive on the intermittent time series, and just to give you an idea what can be done with that. This is also typical for e-commerces, where you have a product portfolio out of 200,000 products, or let's say 20,000 products, and 19,500 products are being sold almost no. And there are only 500 products that drive the whole revenue, and then you have a majority of products that are actually in a similar manner to that. And that is, we need to find ways of coping with that. One way I want to show you today is the Croston Method. This is one of the most classical methods that you can use in order to model intermittent demand. There are further advantages, but I just want to give you an idea of what is possible, and then we can maybe have later on a discussion of what else is also possible in this area. So for the Croston Method, I just I wrote down in the bar the values for the time series, just for visualization purposes. And then what the Croston method does, for example, it models this one time series separately into two time series, meaning the first time series, denoted here with the Q, just holds the non-zero values, whereas the second time series, the A, holds the frequency of how often do non-zero values occur. In the end, these two time series here are fitted separately within an exponential smoothing formula. So this is a really simple formula. And you just get your prediction by dividing the predicted Q value by the predicted A value. For me, it's not super important that you understand every detail of that. There are also further advanced methods from the Croston method, but just be aware of that there are techniques. If you look at data that looked like this before, there are techniques to cope with, and you should not naively just throw anything at it, because this will probably fail. Okay, this is the key message. All right, so we now looked at the data. We looked at certain criteria of the data. So yeah, so let's predict. I mean, what can possibly go wrong? I mean, every data scientist should laugh, because actually everything can go wrong if you're handling a data science project like this. But for now, we looked at the data, and we now just throw models at our problem. And I introduced myself as an AI scientist. So therefore, as a good AI scientist, what I do, of course, I pick all my neural networks that I have, just throw them at my problem, and I just see what comes out of that. And what could potentially come out, I mean, this is a plot that we see sometimes. I have on the y-axis, I have my root mean squared error, and I want to benchmark my NHITS model. This is like a super advanced time series model, NLP based, whatsoever, super nice. The TFT model, which is like a temporal fusion transformer, it combines LSTM, transformer network, so it's really, really hot shit. And I have my XGBoost, probably everybody knows that. So, I mean, I see here my NHITS model performs the best, it's the most advanced model. So I can just deploy my NHITS model, my work is done for today, and I give it to the customer, right? Oh, what's missing here? Does anybody have a clue what could be missing, like, in order to be really sure that this is a good model?
A real evaluation.
A real evaluation, yeah, we'll come to that in a second. Yeah.
A baseline.
Yes, right, okay, I don't have to teach you anything today. A baseline, correct, because having those results, just like that, it doesn't tell you anything. You could be really good, you could be really bad, you could be mediocre in between somewhere, you don't know. So having, for example, what is a really, really good leverage in order to convince customers from the business value you create is when your customer does his own predictions and does its own forecast, and you get the numbers, then if you're lucky enough and you evaluate his own forecasts, it could maybe look something like this. that's the easiest way. If you can show the customer what he does, and what you do with your models, you have such a margin of how you're performing better. This is the easiest win to convince someone that you actually provide business value for your solutions. If you do not have any customer data, any customer forecast, running baselines is your bread and butter. Like, this is something you have to do before every machine learning run. Because right now, looking at this plot here, suddenly we see that our naive baselines, and it could be various different baselines, statistical baselines, whatsoever, they outperform your whole machine learning fancy stuff. And this is not even that unusual that something happens like this. For example, especially for intermittent time series, we see that statistical models actually perform quite well with that. And having those baselines in place is super important in order to set your results into perspective. And you just said have a proper analysis. That's totally true. I mean, we're talking about data sets that are super nice. Having this global summary statistics, just looking at one number in the end, it doesn't tell you like the whole story of the underlying dynamics. Looking, for example, again at the data distribution, we see that we have also again some Pareto optimal situation where only 20% of products can hold up to 86% of the sales volume. And 40% of the products can hold up to 96% of the whole volume, meaning 60% of the products only make up 4% of your sales volume. Ignoring this data statistics in your analysis is you will totally fail by that. So, for example, one possibly classification is by saying I analyze my products based on my volume, or I analyze them based on my variance, or I build some useful product clusters that reveal basically dynamics of the data set and also help you as a data scientist, but also your customer to understand what actually his problem is and how your performance is. And then your performance can look something like this, where you see, for example, oh wow, my deep learning model, my machine learning model does perform very good on A and B categories, but it does really poorly perform on C categories. And this helps you in order to improve your whole time series forecasting engine, basically. All right. So to sum it up, what is very important? What is most importantly, you should always be aware of your data and your underlying data distributions, and choose the appropriate algorithms looking at intermittent problems or this cold start problems. Also, I didn't talk about that, but this can be very promising. You can provide a mixture of models. Combine the predictions and give this as your final prediction. We also see some very positive results there. Secondly, choose some appropriate clusters on your time series data for your analysis, which is what is very important here. Analyzing your model performance only on clusters, it does not mean to only train on those clusters. Like, these are two different things, and we should definitely differentiate here, because training only on certain clusters is not a good idea. You miss a lot of information there. C, running baselines. Before using any machine learning, any deep learning model, before even thinking about that, running your baselines, doing your homework is most importantly, and without that, you're just missing context, and it's hard to convince yourself, your colleagues, your customer in the end. Right, so again, coming back to the initial question, who did vote for A? Nobody. For D? Yes. Perfect. And the ones voting for B, you were right, okay. Yeah, nice. I mean, it's a highly subjective question. You could do...
ChatGPT would maybe tell us B.
We should check. It's a highly subjective question, but this is definitely one of the most key factors that you should do at every beginning of analysis of use case. Yes, that was my talk. I hope some concepts got clear to you, even though you're not even or you're not even working at the moment in this field. But keeping the data distribution in mind, and also like some analysis concepts that you should definitely be aware of. I hope it helps you, and yeah, thank you very, very much for listening, and yeah, I'm looking forward to the pizza and the chat with you.
So thanks a lot, Robert, for the great talk. I think we have a couple of minutes for questions. At this point, there are no questions on Slido, so if you're looking remotely and you want to ask a question, please ask your questions on Slido. But you can, of course, also ask your questions locally here. Who does have a question?
So first of all, thank you very much for the explanation. I could relate to most of the part because I think I'm doing exactly same stuff in my job currently. And just wanted to know your view about how important it is to retrain our model with the errors which you are having in actual, right? So for example, we made a prediction for this month and then we saw some actual. How do you think that the error which came between our actual and predicted values makes sense in this kind of scenarios?
Yeah. I think this is enough, right? So first of all, I think it's hard to give you like this explicit answer of how much retraining you should do. I mean, there are certain papers that tell you, okay, after 4 weeks, after 6 weeks, after 8 weeks, whatsoever. I think first and foremost, what is important to always track and log your real life performance. So because having only your testing data in place or your holdout set data in place, it does not give you it does not ensure that also your model will perform like that also in life. So having this in place is the most important stuff to always be able to analyze also retrospective your results in a real life scenario. I think this is the most important step that you should do. Besides that, I think we saw, depending on the area, depending on the business, that after 6 to 8 weeks, we saw in some use cases some performance dip. So if this is like for us somehow some rule of thumb, especially working in high dynamic areas where it makes sense to retrain. But I think you will see it if you track it constantly. You will see it for each business and each data set yourself. Yeah.
Yeah, that was. Thank you.
Do we have more questions?
Yeah.
Hi, thank you for your talk. So just one question. You talked about like the state-of-the-art models, TFT, NH, and XGBoost. So when it comes to e-commerce industry, especially like fashion retail, where the data is very volatile most of the times, and you hardly have any historical data in many cases.
Yeah.
So from your particular experience, can you suggest which are the methods which really work well for what kind of product categories?
Yeah, good question. So what I would say and what we see is, I mean, there's a lot to say about that. So most important rule or most important fact is the higher your data set, the bigger that your data set gets, the more heterogeneous your data set is. So for example, we have data sets with, or sometimes I work with data sets 10, 20, 30,000 groupings, but I could take a relatively small model since the data set was not that heterogeneous to other data sets. So the data sets, they had similarities. So I didn't need that capacity of a big model to really be able to model all different time series. When we see bigger data sets, more heterogeneous data set, your model just needs capacity of being able to model intermittent, but also take exogenous variables into account, in order to being able to model influences of external data. All this stuff just means that the more complex the problem is, the more data you have, the more heterogeneous your data set gets, the more capacity you need. And we see, for example, that NLP-based NHITs, they're working quite well. Also, they're very effective. You can iterate a bit more faster, I'd say, than with transformer-based methods, because they just need a lot of training time, and you really need to look after learning rates and all that stuff. Then it's yeah. So this is my rule of thumb. There are more advanced techniques. Sometimes also this one global model does not the best job. You need combinations of models depending on what data you're actually trying to predict. But yeah. Yeah.
Do we have further questions?
Yeah, thanks for the talk. I have a question about the cost functions that you use. Do you also sometimes use more exotic cost functions with your customers?
With the customers?
Yeah, maybe someone is asking, okay, RMSE, it doesn't matter to me. I want to make good decisions, as you also outlined. I want to measure, for instance, how do those models help me to make better decisions?
Yeah. So so there's definitely. So first of all, what we see is that the metrics used to evaluate with the customer and the loss functions that you're talking about training our models, they are not necessarily always the same. Having a simple metric function for your customer to be able to explain how good you are in in numbers that are also understandable if you're not like a mathematician or something is very, very important. This has nothing to do with what we use as loss functions. But I think you were hinting on another point. For example, loss functions to see. For example, if over-predicting the demand is more costly for their own use cases than, for example, under-predicting. Meaning, for example, you overstock, okay, you have more cost in, for example, for your warehouse, but under-predicting is like really bad for you since you lose a lot of sales, so that hurts even more than just over-predicting. And on the optimization part, I mean, Fabian is the optimization expert here, but on the optimization part, we use more fancy metrics in order to display our actual value. On the demand prediction side, I think, from my experience, it's better to use more simple metrics and to explain the behavior of your model by that, and not too fancy metrics. I think on the optimization side, it's a little different, right?
And if you look at the coffee bar, custom metrics are really expensive because they always have caveats, and cause like if you optimize for them, always some things that you never thought about before.
Okay, thank you.
All right, we now do have a question on Slido asked by Gus, and I'll try to rephrase it or read it. Do you consider training time and model explanation? Stats and ML models usually trains way faster than neural networks and also helps you to understand a little more the data.
Yes, that is a really good question. So obviously, yes, of course, we include training times when choosing our models. I mean, just thinking about it, training a statistical model can take some seconds, so you do not have to think too much about, for example, infrastructure, how you store your models in the end. You can basically, it's a trade-off, but you can also say, okay, I train my stats models just every time. It doesn't matter about storing. Obviously, for example, when you're using the neural networks, it takes much more infrastructure in order to make those models work. Explainability is a very good topic. I mean, you have some really simple models that are purely that provide some explainability from the shelf. For example, I mean, we're talking about linear models. Obviously, it's easy. You're talking about decision trees where you not really get, it's not super explainable, but you get at least some kind of feature importance. You do not get that from top of the shelf from the neural networks we're working with. That being said, there are also techniques that make your data, that let you explain your model even better, talking about Shapley values or something like that. You can, for example, combine the Shap values with your neural networks, and then you get at least induce some kind of explainability. For us, I think performance is highest prior. Secondly, explainability.
All right, thanks a lot. I would say before we move on, we give a warm hand to Robert.